And your analog lab, in-person lab is on 3rd, 4th of Jan, I think.
Yes, sir.
Fourth and fifth, these two are the dates.
Okay, 4th and 5th. Mm, yes, now my screen visible.
Yes, sir.
Okay. So basically, if we're talking about this particularly question number 1 in graded assignment, okay, I think I upload the solution also. If you have any doubt in the solution, you can ask. The solution is uploaded. Yes, week 10 solution is uploaded on
Didn't check that, sir.
okay. So I will explain that. Uh, Question 1, the battery is 500 mAh charged with 50%. Okay, that means the total current is 250 mAh. Okay, and this particularly 250 mAh current will be, we have to survive with this battery for a 180 days. Okay, so how many hours? 180 days multiplied by 20 hours, 24 hours. Okay, so if we calculate this one, so this is called the standby current. Standby current, or we can say the minimum current. Okay. Similarly, if you are aware that like if I say that 250 mAh current battery is available, so what is the meaning of 250 mAh? What is the meaning of 250 mAh? That means if I required a 250 milliampere current, so the battery will be stand for 1 hour. If I required a 125 milliampere current, so the battery life is 2 hours. Okay, so how many current we required? Minimum current it will be travel, basically it will be delivered by the battery if I have to work for 180 multiplied by 24 hours. Okay, so how we calculate it? 250 divided by 180 into 24. So that is the standby current. Okay, the question 1 is this one. The question 2, the band gap has a line regulation of 2 millivolt per volt. The line regulation of a linear regulator. Now, if you see this one, this circuit, this is also the one question is given similar to this one in a practice assignment. So the band gap has a line regulation. That means the line regulation at this point is 2 millivolt per volt. Okay. Now this particularly 2 millivolt per volt will be applied as a operation amplifier. Now this particularly complete circuit is called the linear regulator. This is the diagram of linear regulator. So what is the line regulation of this linear regulator? That means what is the output voltage of this at this point? Can you calculate it? Yes, can you calculate what is the V out? Yes or no? Now,
6,
Yes, sir.
sir.
One second.
6 millivolt, because this particularly operation amplifier. Okay, if you see the feedback, so this MOS circuit provide the 180 degree phase shift. Okay, if it's provide the 180 degree phase shift, that means here this particularly loop is the negative feedback. This loop is the negative feedback. In the case of negative feedback, what is the condition? We apply the virtual ground concept. And according to the virtual ground concept, the voltage at this point is 2 millivolt per volt. So what is the V out? It is only a voltage divider biasing. So V out is equal to V in multiplied by the addition of these two, or basically V in. If we say the V in is equal to V out multiplied by the voltage drop across this resistor 100K divided by addition of these two. Okay, so V out we calculate as a V in multiplied by 300 upon 100. So it is a 6 millivolt per volt. Now, if we go with the third question, now here the ground mark in a previous question figure is not ideal. Suppose there is a 1 millivolt error between the ground and the ideal ground. Will it impact the output voltage? So basically, it will not impact the output voltage, because if at any point if I say that if only this particularly ground will be behave as a 1 millivolt source, then there is a change in the output voltage. But every ground, I think this ground 1 millivolt, this ground 1 millivolt. Okay, so every ground will be as a 1 millivolt. Okay, so there is no particularly effect of this one. Okay, the variance in the output voltage is percent when the 0.33 in R1 resistance and 0.5% in the R2 resistance is faulty. So we know sigma square del R1 upon R1 is 1 by 3. Okay, sigma square del of R2 upon R2 is 1 by 2. Okay, so sigma square del V out upon V out is equal to R1 upon R1 plus R2 square sigma square del R1 upon R1 plus sigma square sorry, del R2 upon R2. Okay, put these values. Consider R1 and R2 both are equal, because it's not given in this one. So R1 and R2 both are equal. So we calculate the variance. The answer I have changed. I think it is 0.2. Okay, so in the solution part it is correct.
Sir,
Yeah,
how you calculate the 1 by 3 and 1 by 2?
that is
The
a
change.
0.33%, na? So 0.33 is 1 by 3%, and 0.5 is 1 by 2%. Okay,
Yes.
so that's why I am either I can put it in the form of normal form, so I can write it as a 1 by 300. I can write it as 1 by 200. Okay, but again we have to convert into the percentage. So what I do, I just put this value in a percent form. So 1 by 3 square plus 1 by 2 square, and this value is in form of percent.
Sir, but we don't know the values of R1 and R2
But
here.
I think I have already mm, sent a message that R1 and R2 are equal.
Yeah, you sent across that message. So that means that the first proportion should be taken as half.
Yeah, this particularly will be half. Okay, so this is a 1 by 4, 1 by
Are you sharing your screen, sir? I- Yeah, okay. Yeah.
1 by 3 plus 1 by 2. So it is a 5 divided by 24. Okay. If maximum load current delivered to external circuit is 100 milliampere, the load regulation is,
So for the
yeah,
last question, the answer is between point 0.1 to point 0.3.
yeah. The answer
And
is
what we have just calculated is 5 by
5 by 24%. So that is what,
so that comes out to be point 0.2, point
around
0.2, point 0.20833.
208, yeah, 202.21.
Yeah, 0.21. So do we need to convert it into percentage? Like,
It is already in percent.
is it already in percentage?
Yeah,
How
it
to
is
be?
already in percent.
Okay.
Okay,
So it
otherwise
is
what you have to do,
0.21%.
either what you have to do, you can change this particularly in the normal 1 by 300 plus 1 by 200. Okay, so it becomes 5 divided by 2400. Now if I want to convert in percentage, I just multiply with 100. Okay, so it is again a
Okay.
0.21%.
Okay. Okay. Okay.
Okay, now the question number 5. What is the basically load regulation? Change in output voltage when current equal to 0 to current as maximum. Okay, so initially I just assume that current is 0, I is 0. So there is no load. Okay, so output voltage V out is nothing but V in multiply by the voltage drop across this 10 ohm divided by 20 ohm. Okay, so it is just half 2.1 volt. Okay, so when I is 0, V out is 2.1. Now second case is I just consider that there is a 100 milliampere current is delivered. Okay, I am taking the direction outward direction. Why I am taking the outward direction? Because it delivered the current, delivered to external circuit. Okay, so when 100 milliampere deliver to the current, this is the current and resistance. So can I change in as a voltage source? So it is, the circuit is like this one and one voltage source. The current is flowing in the downward direction, so I am taking the direction of the battery is minus and plus. Okay, what is the voltage drop across this resistance is 100 multiplied by 10 is 1000 millivolt. So I am just representing as a 1 volt. 10 and 10. This is the V out. Okay, V in. Now, what is the current? I is V in plus 1 volt divided by 20 ohm resistance. V in is 4.2, so 4.2 plus 1 5.2 divided by 20. So 0.26 milliampere current. Sorry, 0.26 ampere current. Okay. Now if 0.26 ampere current will be delivered, so what is the voltage drop across this resistance? That is 2.6 volt. Now if this is V in, that is a 4.2, out of 4.2, 2.6 is delivered to this point. That means what is the voltage remaining at this point? That is 4.2 minus 2.6. That is 1.6 volt. So when I is maximum, V out is 1.6 volt. Okay. So del V out is 2.1 minus 1.6 is equal to 0.5 volt or 500 millivolt.
Sir,
Yes,
why you take the negative sign as a first
because
first negative?
current is down, current is going downward direction. Okay, so that's why I'm taking the negatives. This one is a, this one. The current direction is again a downward. Okay,
Yes, sir.
so that is clear.
Yes, sir.
Now for a given circuit, the value of R2 resistance is kilo ohm, so that 4.2 battery, 4.2 volt, 3000 mAh battery shelf time is 9 months. Assume R1 is 5 kilo ohm. So basically, we have a 3000 mAh battery. Okay, and what particularly we have to use it as a for a 9 month. 9 month means 30 multiplied by 9 multiplied by 24. So how much current? So it is 3000 divided by 30 9 divided by 24. So it is a 0.46 milliampere. That is the current. Okay. Now that current is equal to V in divided by R1 plus R2. So R1 plus R2 is equal to 4.2 divided by 0.46. So it becomes 4.2 divided by 46. That is equal to 9.13. Okay. Now R1 is 5 kilo ohm, so R2 becomes 9.13 minus 5, that is 4.13 kilo. Any doubt? Now,
So in this question, on question number 6, we were not given the percentage of battery that would be available at the time of
I'm
starting.
giving the 1000 mAh battery now. If it is not given, that means battery is completely charged.
Yeah, yeah. So that was the assumption that we had to make
No, if we are
in
not giving
practice
anything,
assignment and the way it was explained in the lecture.
yeah. If I am giving the 1000 mAh, 3000 mAh
Yeah.
battery, so either I have, if the battery will be charged with some percentage, so I have to mention it. Otherwise, you assume that it is a 100%.
Okay.
Okay, question number 7. In a given circuit, the reference band gap voltage is V to achieve the output voltage. We know the output voltage is 3.5 volt. We have to identify this one. So what is the voltage at this point? So we are saying that that is a Vy. So Vy is V out into this voltage 200 divided by addition of these two particular resistors. 350. Then V out is Vy is 3.5 divided by 200 upon 350. So it becomes 2 volt. That means the band gap reference voltage is 2 volt. Okay. Now after that, if for the same question, if the required voltage is 4.2 volt, the changes in the feedback resistance is what? Okay, so now what we said, this is the 2 volt, that is the fix, but we have to change this particularly voltage. Now this voltage is 4.2 volt. Okay, so here again we know the 2 volt. We say that this is the RF feedback resistance. Okay, so what is the V out? V out is Vy into 200 plus RF upon 200. Okay, now Vy is 2 volt, V out is 4.2. So 4.2 is equal to 2 into 200 plus RF upon 200. Okay, so 2.1 is equal to 200 plus RF upon 200. Multiply this one is the 420 is equal to 200 plus RF. That means RF is 220 kilo ohm. Okay. Initially, what is the value? 50. 150. Initially, what is the value? 150. Now the value is 220 kilo ohm. So how much changes is there in feedback resistance? That is 220 minus 150 is 70 kilo ohm. Okay. So any doubt you can ask me. This is about. And week 11 deadline is today, 18th.
Yes, sir.
Okay.
Sir,
Hmm.
could you go through the content of week 11?
Yes, 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 yes. So, can you briefly tell me, wait a minute, what particularly content is there in week 11? Okay, low dropout regulator, then linear regulator, then switching regulator, okay, efficiency and switching regulator, okay. So,
Sir,
yeah,
so after the revision, I am having a doubt in week 11 practice assignment.
week 11 practice assignment.
Ah,
Okay, okay, first we revise that one.
yeah, yeah. After the revision, can I ask?
Yeah.
Okay, sir.
So basically, if we are talking about the low dropout voltage regulator, so basically, what is the purpose of here? We are discussing two types of regulator. One is the linear regulator and one is the switching regulator. Okay. So the condition of the linear regulator and switching, what is the difference between the linear regulator and switching regulator? First thing is that linear regulator and switching regulator. The linear regulator will provide us the constant output voltage. Okay, doesn't mean that the load required that voltage or not. Whereas switching regulator will provide a constant output voltage as per load requirement. As per load requirement. So what is the meaning of as per load requirement? Like if I have a regulator of 12 volt, but my load requirement is only 5 volt, so it provides the 5 volt. If my load requirement is 7 9 volt, 7 volt, or 12 volt, so as per my requirement it will be provide me the constant. Whereas if the linear regulator is 12 volt, it will provide me the constant 12 volt. Either I required only 5 volt, there is no particular reason. Okay, so in this, it's wait a minute. Mm, yeah. So the professor will be using this voltage control voltage source. Okay, this is the V in voltage, fan gap reference voltage. Now the purpose of this circuit is that the output voltage we are getting at this point, V out, is not dependent on V in voltage. Okay, so the reason of that is if battery voltage V in is the basically the battery voltage. If battery voltage reduces, the output voltage is constant because this particularly battery voltage is only used to operate the band gap reference voltage. Okay, now sorry, voltage control current source. Okay, now the condition of this particularly voltage control current source is that if VSD voltage is greater than V threshold voltage, okay, then the voltage is basically the function of current. Okay, and if VSD is less than V threshold voltage, okay, it behave as a open switch, now what is the VSD? This is the most device having the three terminals: source, gate and drain. So basically VSD is the voltage difference between the source and drain terminal. Okay, so VSD is basically this one. Okay, now if yeah, this voltage is the function of current and it behave as a open switch. Yeah. Now if we use this one like a circuit, that this is my band gap, or in I change this particular circuit in this way, like this is my V in. Okay, so the difference between V in and V out is called the dropout voltage, VDO. Okay, dropout voltage. As we already discussed this one, we if we have a battery, so V in is nothing but the battery voltage and V out is the regulator voltage. Regulator voltage. The difference between the V in and V out is the voltage, low voltage drop. Okay. Now there are multiple VDO are available in the market. If the VDO is less, dropout voltage is less, the linear regulator is good. Okay. Normally in the case of circuit, the VDO will be lies from the 200 to 300 millivolt. That is all dependent on the application. It is below this video will be also available and above this video is also available, but the condition is that video should be less, it is better. Okay. Mm, after that, yes, after that the professor discussed some linear characteristics of the low dropout regulator. In this particularly characteristic they have discussed one particular data sheet is TLV7 34P, oh, sorry, I think 743P. Okay, so this is the one linear regulator, low dropout regulator, and this is available in the market 7418, also available TLV. So basically this three is defined as it has a 300 millivolt dropout. 18 is defined as a 180 millivolt dropout. So the name of this ICs is in this way 743 and 7418 is available. So this 743P is discussed by the professor, that is available in the 300 300 milliampere. TLV 743P. Yeah, 300 milliampere, not millivolt. 300 milliampere. But if you see here, this dropout voltage is also a function. The voltage is function of the current. 125 millivolt at a 300 milliampere. Okay, so 300 milliampere and 180 milliampere. So that particularly is a voltage is a function of current. So this 125 millivolt is at a 300 milliampere. Okay, along with that, some particularly parameters are discussed by the professors. mm, where they discuss this particular dropout voltage, start time. Okay, so this particularly will be discussed by the professor in lecture 2. In lecture 3, low output impedance of LDO linear regulator. So now the low output impedance. So the low output impedance. Basically, for the low output impedance, we are connected like we have a dropout voltage, mm, like this is we have a linear regulator. Okay, that is behave like this one. This is uh, become negative. This become positive. Grounded. This one. Yeah. So like if we are taking that, this is my linear regulator circuit. Okay. Now we have a output impedance. So this output impedance plays a very crucial role. Why crucial role? Because if we have a, this is the gain A, this feedback circuit has having the gain B, so the loop gain is A beta. If the loop gain is A beta, what is the value of R out? R out is nothing but RO upon 1 plus A beta. Okay, and if we are talking about what is the gain beta, mm, sorry, what is the gain beta? So if I say this is the R1, this is the R2, so the value of beta is the voltage drop across this one, R1 upon R1 plus R2. So R out is RO upon 1 plus A beta. Okay. Now if I increase the beta value or increase the gain value, what is the effect of this one? My R out will be reducing, because if beta increases, A beta factor increase, 1 plus A beta factor increase, and R out decrease. Now we are saying, hmm, hmm, after that, what is the effect? I think they discuss the effect of frequency on versus loop gain. I think this is, yeah, frequency versus loop gain they have discussed. So mhm, yeah, so they discuss that A beta is high at a DC and A beta is less at a AC signal. Okay, so how this particularly condition will be appear? Initially, what we assume that R1 and R2 both are pure resistive. If both are pure resistive, no effect of frequency will appear. Okay, but if in place of R1 and R2 we are taking the Z1 and Z2, the behave is a pure or not pure. We are saying the resistive and capacitive. Okay, resistive and capacitive. So if this thing will be happen, so what is the effect of this one is, as omega is increases, Z1 and Z2 decreases. Okay, if Z1 and Z2 will be decreases, the beta is reducing, and if beta is reducing, the loop gain A beta is reducing. If loop gain A beta is reducing, Z out increases. Okay, so with increase in the frequency, beta is reducing, A beta is reducing, and Z out is reducing. So if I draw the curve between the A beta and the versus frequency, this is the omega, this is the A beta. Till at a certain frequency, this is the effect, and after that particularly it will be start reducing. Is it clear? Any doubt?
No, sir.
Okay. Now, if the value of Z out is increases, what is the effect of this one? If I draw the curve of Z out, so my Z out should be like that at a certain frequency, and after that we start increasing. Okay, so this is my Z out with respect to the frequency, because A beta and Z out both are reverse. If A beta is reducing, Z out increases. If A beta is increasing, Z out reducing. Okay. Now if I say I have taken this omega and I have taken as a Z. That Z is nothing but a capacitor. Okay, so when the omega is increasing, 1 upon omega c is reducing. So if omega is increased, 1 over omega c reduce. Okay, so if we have a circuit minus plus minus, so this is my capacitor. Okay, now if I introduce one capacitor at the output side, so what is the effect of Z out? I just draw it here. This is my omega. So the effect of one capacitor is that when I increase the frequency, the 1 upon omega c, if I say that this is a capacitor, so 1 over omega c. Okay, but what about the amplifier? What particularly basically the output? If my Z will be reducing, or I can say my A beta is reducing, what is the effect? My Z out is increasing. So I can create a Z out like that. Okay. So the overall Z out is that when the Z out is increasing, so it will be increasing, but because of this capacitor, it will be start reducing again. So this is my Z out. So that particularly amplifier will be a work on this particular range. This is the Z out offset. Okay, Z out offset. Why? Because this capacitor, like I am working on a frequency, like I just say that the capacitor value is 1 millifarad. Okay, so the effect of this capacitor will be arises. What is the effect of this one is the when I have the frequency 1 kilo ohm multiply by the 1 millifarad, what is the Z value? Z value is 1. Okay, so I say that if I am using the 1 millifarad capacitor, it will be 1 kilohertz. Okay, if I say it is a 1 microfarad capacitor, so 1 microfarad, so I have take the frequency omega f is equal to 10 raised to 5 6 upon 2 pi, or omega is 10 raised to power 6. Okay, so what is the value of Z impedance of this particularly capacitor? Z is equal to 1 over omega c, so 1 over 10 raised to power 6 into 1 into 10 raised to power minus 6, that becomes 1. So this value will be 1 megahertz. Okay, so at the value of omega 1 megahertz, it provide me this one, and after that it will be, because of this capacitance, it will be start reducing again. So this is the Z exactly. Now it will be work only this range. It will be work only this range. This range. But I want that my regulator will be work for all frequencies. Work for a span. Work for a long span frequency range. So what I do, in place of 1 microfarad, I use two capacitor in the output side, and one is the 1 microfarad and one is the 10 microfarad. Now if Z is 1 over omega c, capacitor is 10 microfarad, so 10 into 10 raised to power minus 6. Now my frequency is 10 raised to power 5, that means 100 kilohertz. So my frequency is 100 kilohertz, so it will be start working in a 100 kilohertz. Okay, so my spam is increases. Initially that is work for 1 megahertz, now it will be work from 100 kilohertz to 1 megahertz. 100 kilohertz to 1 megahertz. Why? Because 100 kilohertz because of this one, and 1 megahertz for 1 microfarad. If I increase the span more, so I have to introduce more capacitors. So like for example, I am using one capacitor 1 microfarad, one capacitor 100 nanofarad, and one capacitor 10 nanofarad. I am using the three capacitor. So when the value of Z will be 1 for all. For this one, I know at 1 megahertz, omega is equal to 1 megahertz, Z value is 1. For this one, I know when omega is 10 megahertz, Z value will be 1. For this one, I know when omega is 100 megahertz, the value of Z will be 1. Okay? So we have the spam now. What spam we are getting now? The omega, this one particularly working on this one. 1 over omega c. Okay? When c is 1 microfarad. This is when C is 100 nanofarad, and this C is when C is 10 nanofarad. Okay, this is my Z out. So basically my spam will be increases. This one, if I draw with the other symbol, so my spam Z out spam is increasing. Why? Because of 1 microfarad it will be start working at 1 megahertz. For this one it is working as a 10 megahertz. After 1 megahertz it will be start increasing, but again there is a effect of 100 nanofarad capacitor. So again at 10 megahertz frequencies, particularly Z value is minimum. After that again it will be start increasing, but because of 10 nanofarad capacitors again it will be reducing at a 100 megahertz. Okay, and after 100 megahertz it will be start increasing. So now my spam is 1 megahertz to 100 megahertz. This is the spam. Okay, so in the output, if I am using a multiple capacitor with a different value, we are getting the maximum spam where this particularly will be operating. Now if I know this is my capacitor. Okay, so what is the equivalent resistance of the equivalent circuit of this one is that if I am using the capacitor, so this particularly SMD component, this particularly leads, this particularly terminus will be behave as a inductor. Why? Because it is a wire. When
Sir,
the current is flowing from that,
sir,
yes,
one small note.
yeah,
Sir, previously you have drawn the graph, right? The Z out.
uh,
Yeah, when we have three capacitors in parallel.
yeah, yes,
I mean, how is that effect being cancelled out? Because the three capacitors are in parallel in the sense
yeah.
the
Three
capacitances
capac-
get add up.
yes, three capacitors is parallel. One capacitor will be effectively working on which frequency?
Okay, so if I mean if one of them is low, it shows the impact on the other.
Yeah,
Then
you
what
know
about it, the DC?
basically if you are aware about the Bode plot,
Yes, sir.
okay, like for example, if I have a component 1 plus 1 by 2s, okay, so what is the effect of this Bode plot will be, this particularly pole will be having at omega is equal to 2.
Yeah.
Before this omega is equal to 2 there is no effect, and after this one the effect will be arises. So similarly is this case, like if this particularly capacitor impedance is minimum at a 1 megahertz, so what is the effect of this capacitor at what frequency? Only 1 megahertz. So we are considering at 1 megahertz is provide the minimum Z value. Okay, now after that one there is no effect. Why? Because when we increase the frequency, my Z out will be increases. My basically Z out will be start increasing. Why? Because Z out is equal to Z naught upon 1 plus A beta. So basically, if I am saying that 1 uh, into 10 raised to power 6 radian per second is my omega. Okay, so at this particularly frequency, my beta value will be minimum. If beta value is minimum, my Z out will be maximum.
Yes, sir, got it.
Okay, So only
Okay.
at particularly that frequency, this effect, this particularly capacitor will be creating effect. But after, if I am increasing the 2 megahertz, what will be happen? It will be start increasing again.
No, no, no.
I just give it with this one. I just give a example of taking this one. Like for example, this is my value. Okay, this is my capacitor. This wire, this is wire. When the current will be flowing, there is one inducting effect is created. So can I replace this particularly capacitor with the inductor, with a capacitor, and with a resistance? Lead has some resistance. When the current is flowing from the lead, it will be produce some inductive effect and capacitor. Okay. Now, when the Z value is minimum, what is Z? Initially, what is Z? What is the Z equivalent? Yes. What is Z equivalent?
R square plus
R square plus J omega L minus 1 upon omega C. Or we can say
yes,
that
sir.
if I take the magnitude, so I am not taking the J, omega L minus 1 upon omega C square. Okay. Any doubt?
No, sir.
This is the omega L, J omega L. This is the 1 over J omega C. This is, sorry, this is 1 over J omega C, and this one is the R. So Z is nothing but R plus J of omega L minus 1 upon omega C. If I take the magnitude of this one, so what do I, how we take the magnitude? Real component is square plus imaginary component is square. So omega L minus omega 1 over omega C square and root of this one. Okay. Now, if I am taking the omega is 1 megahertz, okay. In this case, what will be happen? I suppose that this particularly omega is my normalized frequency. Okay. So what is the effect? In this frequency, my value of omega L is equal to 1 over omega C. Resonating frequency, we call them the resonating frequency. So if omega is 1 megahertz, then that particular frequency is the resonating frequency. So omega L is equal to 1 over omega C. So what is the value of Z? Becomes R. Now, if I increase the value of omega, what will be happen? This component will be increases, this component will be reducing. So my value of Z will be start increasing. Okay. So I draw the curve. This one. Okay. And that particularly is the resonating frequency for 1 microfarad capacitor. Clear? Now if I increase the value of capacitor. So basically how we calculate the resonating frequency? The omega is 1 upon root of LC. Now if I decrease the value of capacitor, my value of resonating frequency will be increasing. So if I increase a capacitor value, this is a 1 microfarad. If I increase the capacitor value, so it will be shifted the resonating frequency. So maybe this is the more than 1. So 1 plus del x. Okay, and third case, when I increase one more particularly capacitor, so the resonating frequency will be increasing. So it becomes 1 plus 2 del of x. Okay, I am taking some simply. The value is anything. So it is a 1 resonating frequency because of 1 microfarad, resonating frequency because of more than, sorry, the value of frequencies. If I am taking, this is the f, so this is f plus del f, and it is a f plus 2 del f. Okay, so my capacitor effect will be increased. Now if I increase the value of frequency, so effect of first capacitor will be reducing. Yes. So if I am saying that this particularly capacitor will be lower at this frequency, and after that it will be effect created effect, after it will be start increasing. But when it will be start increasing, again we are getting a 10 microfarad sorry 10, or basically the 100 nanofarad capacitor. So again it is start decreasing, again it is start decreasing, again after that it will be start increasing, but again we are getting a 10 nanofarad capacitor, so it's again started reducing, and after 10 nanofarad capacitor there is no more capacitor, so it will be starting increasing. Clear?
Yes, sir.
So basically we have to reduce the value of Z out. Why the value of Z out is reducing? Why the value of Z out will be reducing? Yes, the question is why we focus on Z out should be reduced. Yes, anyone?
Sir, because we are using different values of capacitors.
That different value is using for the reducing the Z out value. So, but the condition is why Z out? Why we focus on Z out to should be reduced? The question is this one. This Z out is reduced. The Z out is reduces. Sorry, I will take a different. Z out is reduces to by sorry reduces by using different value of capacitors. But why Z out reduce? Why we focus on that Z out should be reduced? Any idea? Gaurav, Satyam, Subhash, any idea? Why we focus to reduce the Z out value?
Sir, because we are considering this as an voltage source, a typical voltage source will be having an low impedance, low output impedance.
Yeah. So we are considering that as a voltage source. That provide me the constant voltage. Okay. So our voltage regulator, like for example, I have a 220 volt AC signal. Okay, and I have to convert it into a 12 volt. So what we do? Initially, we use the transformer to reduce the voltage up to the 12 volt AC or 12 volt, 15 volt. That is up to you. Then after that, we are using a rectifier circuit. Okay, after that, what we are using, the rectifier circuit will be providing me the from AC to the pulsating DC, and after that we are using the regulator circuit that provide me the pulsating D to DC to the constant DC signal. So basically, it is behave as a voltage source for us. Okay, and the voltage source have the minimum Z out value. So that's why we are concerned about the Z out value. Okay. So to reduce the value of Z out, we are using a multiple capacitor. So the response for the all frequencies for the DC, we know the behavior of the at the DC. For the DC, the AB is high. Okay, for the DC, AB is high, and if AB is high, Z out is less. But if you are using the AC signal, so in the AC signal, AB is that is a loop gain is basically less, and Z out is high. So to reduce the Z out, what should we do? You are using parallel capacitor at the output terminal. Okay, so if you are using a single capacitor, that particularly capacitor will provide a low Z out for a constant single frequency. Like if you are using a 1 microfarad capacitor, so that my 1 microfarad capacitor provide me low Z out at 1 megahertz only. Or we can say if we are the 1 megahertz the center frequency, so I am just saying the 9.9 to 1.1 megahertz. But what about other frequencies? Okay, if I provide the more than that frequencies or less than that frequencies, so the Z out value will be increasing. So what we do, we have to operate my device for a longer frequency band. So we are using a multiple capacitor. Okay. After that, mm, I think, yeah. After that, the efficiency. Efficiency is nothing but the output power upon input power. Okay. Linear regulator will provide me the constant voltage for all particularly time period. Okay. So the output power, if I'm saying that is the voltage multiplied by the current output voltage V out upon multiplied by the out. upon V in multiplied by the IA. Okay, that is the efficiency. Okay. Now, along with that, the professor discussed the switching regulator. In the switching regulator, I just already told you that if we have required the 12 volt, the regulator provide me the 12 volt, so it is not compulsory that this 12 volt will be provided for a odd duration. Sometimes it will be provided less than 12 volts. Sometimes it will provide a 12 volt for a, like if we are talking about a AC supply. Okay, so if I say that my AC will be working on a 12 volt, 12 hours. Okay, it is working on a 12 hours, so I can't say that for a complete 12 hours that particularly AC will be using a 1.5 kilowatt hour unit. That is the power required for all 12 hours. That is not compulsory. Okay, that is not compulsory. Initially maybe that will be required a 1.6 kilowatt hours. After that it will be reducing because my room is chilled now. Okay, so there I can drop down my particularly power. So after that maybe 0.8 kilowatt hour. Again my particularly AC is, my room is more chilled, so it I required a 0.4 kilowatt hour, 0.4 kilowatt hour. So that power I can require. Okay, 1.6, 0.8, 0.4, 0.4. So the switching regulator is similar way. Switching regulator is just a similar way. So along with the output power, we just multiply with the duty cycle. Why? Because this output power is not provided for a complete duration. It may be provided for a half of the time, it may be provided 4.4% of the time, total time period. So that is all up to depend on the which particularly device where we are using the switching regulator upon input power. Output power into duty cycle. uh, I think the duty cycle in this is in denominator. Hmm, we are using one storage device. Hmm, I think at the duty cycle is in the numerator part. Mhm. I am not much sure about it. If I say that efficiency, if I am talking about the efficiency, yeah, that is in the denominator part. Duty cycle. That is the denominator part. Yeah. So the difference between the linear regulator and switching regulator is there is a one major effect of the duty cycle, and due to this duty cycle, the efficiency will be increases. The efficiency is increases because, as we know that the duty cycle is for the ideal case or for the some certain cases the duty cycle is 1, otherwise the duty cycle is less. That will be increase the efficiency. That is all about the switching regulator. Mm, okay, and in the last professor discuss I think one particularly model system C30 I think, where tear down it will be shown to you. So that is all about week 11. If you have any doubt you can ask me. Yes, if you have any doubt you can ask me.
Sir, in practice assignment, first question, can you once explain how to do?
Hmm, practice assignment. Hmm, if the noise voltage in the input supply is 5 microvolt at 100 hertz frequency, the noise regulator or the output of TLP4. Yeah. Hmm, so basically, I think, yeah, I just show you the, yes. Okay, this is the data sheet. Uh, yeah. What is the PSRR?
Power supply rejection ratio.
Power supply rejection ratio. What it shows? It is a basically output upon input voltage noise power. Okay. So for 100 hertz, this value is 68 dB.
Sir,
So
did he teach about this in the lecture?
yeah, professor discussed this thing. So 68 is equal to 20 log 10 V in upon V out. So that is mm, 3.4 is equal to log 10 V in upon V out. So V in upon V out is 10 raised to power 3.4
Oh, my phone class. Oh,
and V out is, yeah,
sorry, sir.
now clear?
Mm. Now clear, sir.
10 raised to power 3.4.
Sir, in exam they will give these values, a VSRR value and all.
Yeah, if there is a question in the exam, it will be given.
Okay, you will give the whole data sheet or
You just check it when you are giving the exam. But
sir?
that is sufficient for you.
Okay, sir. The amount of I don't remember sir explained this VSRR. Actually, this
PSRR,
VSRR comes under this S parameters and all, right?
no, PSRR, that is not in S parameter.
Yeah, but I don't remember sir saying in any lecture.
I think the professor discussed this one. So it is a 0.19 microvolt.
Sir, could you explain that once again? The question.
First question,
Yes, sir.
I just explained, na? The 68, basically, if you check the datasheet 743p, so it is a 68 dB at 100 hertz. So you have to check at what particular frequency we are talking. If we are talking about the 100 hertz, it is 68. If it is a 10 kilohertz, 35, and it is a 100 kilohertz, 28. Okay, so the value is 68. So 68 is equal to 20 log V in my V out. Okay, so it is a 3.4, and we can calculate the V out value, the noise power, noise voltage at the output side.
Yes, sir.
Okay,
Sir, and the last question.
last seventh question.
Yeah, sixth and seventh, any one of it.
The closed loop amplifier has a single pole of roll off with a bandwidth of 5 kilohertz. If we ref as the 20 millivolt of the noise at 2 kilohertz, the noise at P out will be. Now there is the one thing is important, that your roll off will be 5 kilohertz.
Sir, actually, in our assignment, it is given as 10 kilohertz instead of 5.
That is all up to. I'm not in a practice assignment.
Yeah, but the key is given the same as it is given here.
Okay, that is all. There is no particularly. So basically, what is saying that a single pole roll off with a bandwidth of 5 kilohertz. That means before 5 kilohertz, it will be behave as a operation amplifier. Okay. After 5 kilohertz, we have to check what is the basically working of that one. So
So how can we check it?
yeah, it is given. It is given that a 5 kilohertz. So before 5 kilohertz, it behave as a ideal amplifier. Okay, and after 5 kilohertz, if the frequency is greater than 5 kilohertz, it will be behave as non-ideal amplifier. Okay,
Yeah, sir.
so if we have a 5 kilohertz, so we are giving that the V reference is a 20 millivolt. That means this is a 20 millivolt noise. Okay, what is the output voltage?
4 times this input.
4 times of 20 millivolt.
Yeah,
It is 80 millivolt.
input onto beta.
Okay, yeah. How it is 80 millivolt? Because the gain is 1 plus RF by R1 into
Yeah.
V in, that is equal to V out. Okay, RF is 30 and Rin is 10. So it is RF upon R1, 3 plus 1, 4 multiplied by the V in. So 20 millivolt multiplied by 4 is 80 millivolt. But now after 5 kilohertz, it will behave as a non-ideal amplifier. So what is the meaning of non-ideal amplifier? What is the basically output voltage at the non-inverting non-ideal amplifier? V out is equal to V in, sorry, A upon 1 plus omega n by S. Okay, single pole transfer function is this one. V out by V in, sorry, not V in, V out by V in is A upon 1 plus omega n by S. Now what is the gain? The gain is 4. 4 upon 1 plus omega n by S. What is the omega n and what is the omega S? Anyone? The
How
pole
did we get
plus
this 4, sir?
1 plus RF by R1, this is the gain.
That is beta, right? Oh, okay.
That is gain.
No, no, no. Yeah, gain. I mean, that is the gain only if there is a virtual short.
There is again a this particularly condition is not defined that it is a virtual short or virtual open. But if it is a working in the inverting and non-inverting mode, so what is the gain? 1 plus RF by R1. Okay.
Okay, sir.
Now what is the omega n and what is the S? That is the omega n by S or S by omega n? I think that is S by omega n. Omega n by S is the gain. Okay. Now omega n is what? That is 5 kilohertz because it is a roll of frequency of a single pole. So omega n is 5 kilohertz. And what is S? S is here is my cursor. Yeah. So 4 upon 1 plus S is j omega upon omega n. So V out by V in is equal to 4 upon 1 plus j omega is 50 kilohertz. So either you can put a 2 pi into 50 k upon 2 pi into 5k. So k and k cancel out, 2 pi and 2 pi cancel out. So it is 4 upon 1 plus j of 50. Sorry, j of 10. Okay. And the magnitude of this one is 4 upon, if I take the magnitude, so root of 101. That is nothing but V out by V in. So V out is what? V out is V in multiplied by the 4 upon root of 101. V in is 10 millivolt. Okay, so 10 multiplied by 4, 40. So V out is equal to 40 upon root 101. Hmm, That is, I think, 4 millivolt, not 4 millivolt, not 0.398. It is around 4 millivolt. Okay,
Yes, sir. So
if
this is a standard formula.
yeah, standard formula that you are using that you are under basically uh, learn in week 7 or week 6.
Yes, sir. Weeks, yeah.
Okay, so we are using the standard formula. Only use this value, this particular formula, and putting the values. Okay, if it is a 50 kilo ohm and 10 kilo ohm, if it is a 50 kilo ohm and 10 kilo ohm, so what is the value of A is 6.
Yes, sir.
Any other doubts?
Sir, the duty
Yes, sir.
cycle question is the key, right?
Hmm?
And that the fourth question.
The fourth question, yes.
So
Mm,
the output power by input power. So 1 volt by 3 volt divided by the duty cycle,
yes.
20%.
For the given waveform, the efficiency of the switching regulator is yes. P out is 1 1 divided by 3 into, and duty cycle is 0.4. So 1 divided by 1.2, it is around mm, 1 divided by 1.2. So it is around 0.83 or 83.3%.
Sir,
Yeah,
how we calculate the duty cycle is equal to 0.4?
that is the duty cycle is what? T on upon T on plus T off. Okay, so the particularly pulse will be giving from 0 to 2 or either from 5 to 7. So on time is 2. Either I am not giving the unit, it is a 2 second, 2 millisecond, but it is always a 2. If I am talking a 2 millisecond, so I am taking a 2 millisecond. And T on plus T off, that means from 5 to this point, that is a 5 millisecond. So millisecond and millisecond, it will be cancel out, so it is a 0.4. Okay,
Not getting, sir.
not getting.
Yes, sir.
Okay, so basically duty cycle formula is T on, that means on time upon on plus off time of a single cycle. Okay, so if uh, basically if my I see that my waveform will be repeating by this time period, again this waveform will be repeating by this time period and so on. So I am taking one cycle I am taking from this to this or from this to this. Clear? For how much time it will be on? It will be on for from 5 to 7. It will be on for this time duration, that means from 5 to 7, that means 2. Either the value will be in millisecond, either the value will be in second. Okay, so basically duty cycle is a unitless quantity because the unit numerator and denominator both are in time period, so unit will be cancelled out. So either the unit will be millisecond or either the unit will be second. There is no effect of that part. And what is the t on time period is 2 second, and t of time period is from 7 to 10 plus 3 millisecond or second. So that is 2 divided by 5, that is 0.4. Okay.
Yes, sir. And sir, here we take first waveform also, first
You
cycle.
can take anyone. You can take anyone. Any particularly cycle you can take from 0 to 2,
Yes, sir.
and because if you are confusing that there is no particularly value is given before this particularly point, we don't know. uh, I forget to add this value. I forget to add this value. Yeah, this value is 0, but I forget to add this value. So if this value is given, so I can take the first cycle or the second cycle. That is all up to you.
Yes, sir.
Okay, so now it's fine. Any other doubts?
Yes, sir. No, sir.
Okay. So on Friday, if you have any doubt, we can meet on Friday with your doubts, or probably I will share by today night, or probably today night. I will share the tutorial sheet. So you can solve it, and if you have any doubt, you can ask.
Yes, sir.
Okay. So thank you.
Thank you, sir. Good night.
Good night.
Thank you, sir. Good night.
Good night.